So again, aloha mai kako. Today we have a presentation by Becky Ostertag. Her presentation is titled, What are lessons learned, or how can long-term forest managing monitoring data from the Hawaiʻi Permanent Plot Network inform management? And so with that, Becky, you are able to start whenever you're ready.
Okay, great. Thank you so much for everyone being here. Aloha kako. And there's many people that have been involved in this Hawaiʻi Permanent Plot or HIPPNET project over the years. There's some of them listed here, but there's many others that have played roles, large and small, and I just want to acknowledge all of them, as well as all of these different funders. And I wanted to just briefly start with my moku auhau. This is my four grandparents at the top, all that were immigrants to the US. And I'm the older kid there in the middle, and grew up in Chicago. And then on the bottom is my academic moku auhau, where I did my undergrad, my PhD advisor, Jack Putz, and then three people that were really instrumental during my postdoc. And Ariel Lugo is someone here that maybe people in Hawaii have heard of, who has done a lot of similar work in Puerto Rico. But for me, I've been in Hilo since 2001, and it is where I feel the most local and the places that the Aina calls to me. So these are pictures of forests that inspire me, Vai that inspires me, and the mountain, and of course Kilauea, and then my office here with the nice rainbow over it that I caught on one day. So I'm really happy to be here and talk about some of the forests that we're passionate about and ways that we can think to try to help these forests using tools, scientific tools to collect data that we think can be used to help better manage these resources. I think everyone's very familiar with the ideas that tropical forests are extremely diverse, extremely productive, and extremely carbon rich, and that's especially true of the wet side of these forests. But even the dry forests have very special properties and unique diversity. Permanent plots, which are these long-term study units, provide research opportunities that take advantage of spatial variation, temporal variation, which is really a big advantage of these long-term plots. And they can be really crucial infrastructure for research and management. And Hawaii is a great place for this kind of permanent plot network because we have kind of special, well, we know they're special. We have very special tropical forests that we have a lot of pride as part of our cultural and biological heritage. But the Hawaiian forests also globally are really low in total number of species, but they're very variable. They're very high in endemic species, very variable in climate, and they're ideal for long-term study. Gonna be talking, our Hawaiian forests are part of this global plot network called Forest Geo, formerly the Center for Tropical Forest Science, that's run by the Smithsonian. And it's a network of plots around the world. It started out in the tropics, and then a decade or so ago started including plots in the temperate zone as well. And right now there's more than 7 million trees that are tagged that are part of this network in 27 different countries. So it's truly a global network. And the advantage of being coordinated by the Smithsonian and being in this network is that we're all looking at forests in the same way, using the same methodology with the same kind of data standards. Let's see if I can get this to go forward again. Okay, and the mission of Forest Geo is to understand diversity and the dynamics of these forests and to strengthen the global capacity for forest science. So One of the goals in this network is to be able to catalog many of the Earth's major forest types. Another impetus for setting these up is that they're large plots, so that they capture a high number of stems and a high number of species in a given area. All the stems 1 centimeter or greater in diameter are tagged and marked, and about 12,000 species, or about 20% of the world's world's known tree diversity, can be found in these plots. So that's pretty striking, that how representative they are. And you can see in this graphic here that about a third of the plant genus, the different genera of the world are represented, and many families of the world are represented as well. So this is a great research platform because it helps build significant research infrastructure, and it's led to a large number of publications. The first plot was established in Panama on Barrow Island in the early 80s, and it's just grown from there. And so we are very excited and happy that in Hawaii we are part of this network, because we represent some very important plots within this kind of network. But also, just for Hawaii by itself, the Hawaiʻi Permanent Plot Network, or HIPPNET, has the ability to be a vegetation climate observatory and allow us to build capacity to understand, conserve, and manage Hawaiian forest ecosystems in what we know is a rapidly changing world with climate change, invasive species, and other threats. And so these plots, while they're valuable in a global context, and they've been part of a couple dozen or so global studies, we also, today I'm going to focus on their value for Hawaii and what we look at in these plots and how they could potentially help inform the management of our forests here in Hawaii. So the HIPPNET network was started in 2008 with the help of EPSCoR funding, which is a National Science Foundation program to help build research infrastructure across states. And we set this up as an ecosystem climate observatory. And these permanent plots are arrayed across a matrix of temperature and precipitation gradients. So we wanted to get different climate zones, which also represents different forest types. And so we have 4 of these different plots that are part of the HIPPNET network. We have years now with spatially explicit demographic data and some ecosystem level data. And as I mentioned earlier, part of the methodology that's in all of the forest geoplots is that all trees that are greater than 1 centimeter or greater in diameter are tagged, mapped, and measured, and they're followed through time. And what we're doing here in Hawaii, which is not done at every plot, but we have the ability to do it, is to pair that with state-of-the-art climate measurements. Some of the sites have towers. 2 of them have towers that go above the canopy. And these are really important for estimating some key carbon flux measurements. And 2 of the stations have these on-the-ground climate base stations where the vegetation is not very tall. These are the 4 plots that are part of the HIPPNET network. Our 2 largest plots are the ones that are part of the Smithsonian network, and the other 2 plots are not in the Smithsonian Forest Geo Network, but are part of our HIPPNET Hawaii network. So Laupāhoehoe is a montane wet forest, and that's at about 1,100 meters elevation, and that's our most species diverse plot with about 21 species and about 12,000 marked individual trees. And that's a 4-hectare plot. Our other 4-hectare plot is in the dry forest in Pālamanui, which is much lower elevation, about 240 meters, and much drier and warmer. And this has 15 tree species and a few more stems than the Laupāhoehoe site. And then we have 2 smaller plots, Puʻuwaʻawaʻa In the sanctuary is montane mesic forest, and that's a 1 hectare plot, and that's about 1,750 meters elevation. And then we have the Māmalahoa plot, a little bit off the side of the Māmalahoa Highway, which has very few species, but represents a more lowland, dry woodland type site. And that's also a 1 hectare plot. So what I want to do today is, rather than talk about some of the other things that we've talked about in the past, is talk about some vignettes about how we can use these long-term permanent plot data to inform some kind of management questions. So I'm going to talk about 4 different vignettes here on the koa looper moth, interannual climate variation, pig damage, and abundance of weeds. And right here is just a picture of our grid system, so that you can get a better sense. Our plots are square, and for the 4 hectare plots, for example, the 4 hectare plots have 10 different columns, and then they also have rows. So we have these squares within it, 100 of these quadrats, they're called. And then within that, there are subquadrats. So there's 16 subquadrats within each quad. And we use that to keep track of where all these trees are and to be able to map them. And this grid is very important understanding to figure out our way around when we're out in the field, because it can be quite confusing. Okay, the first story I want to talk about is the koa looper moth. This is an endemic moth, Scotorithera, and it has been known to hit koa trees in the past. In 2013, there was a very large defoliation event, probably the largest one that's been documented, since we've been recording these kinds of things. And from a DLNR fact sheet, it suggested that about 2,500 acres of koa forest was defoliated, making this one of the largest ever documented, as I mentioned. And so the moth eats a lot of the leaves, and the trees really lose much of their cover. And the value of having these long-term plots, which is something that other people didn't have the capacity to do, is that we had information on the koa trees before this moth outbreak and after this moth outbreak. So we see, a tremendous amount of defoliation in the koa forests on this island. And we really want to understand, how bad is that? Is this something that we should really be worried about? Or is this something that our forests can recover from? So what we did was to be ready and take advantage of what was going on. We went to Laupāhoehoe, which was where most of our koa trees were, although there's some in the Puʻuwaʻawaʻa sanctuary as well. That plot has a lot of koa, but I'm not going to present on that data today. In June and August of 2013, during the outbreak, we went and we assessed the trees for defoliation. We made an index from 1 to 4, with 1 being no sign of herbivory by the moth, 2 being 50% or less of the canopy being lost, 3 being 50 to 90%, and 4 being greater than 90%. So we have an index of the amount of damage or defoliation from the moth. And at Laupāhoehoe, there was 149 koa trees, and almost all of them were hit. So there was 1 tree that had no signs of herbivory, and the rest were hit with herbivory, and most of them were 4s and 3s, and just a few trees were in this less than 50%. So it was a pretty significant defoliation event from the moss. And we also found here that the smaller trees in diameter had lower amounts of defoliation. So the moss were hitting the larger canopy trees more than the smaller trees, at least in terms of the amount of damage. So one key question we had, is this going to be a mortality inducing event by having this defoliation in many cases of the entire canopy? And what we found is there's some differences in the mortality before and after the moth outbreak. 2013 was our measurements that occurred before the moth outbreak, and we had 3 trees of koa trees that died naturally in that period. After the outbreak, we had 20, and by 2016 we had 4, and 2019 we had 5. So in these different periods, there's a slight increase in the mortality after the moth outbreak, but the numbers of trees are small. So you're saying 1 more tree died, then maybe 1 to 2 more trees died, than sort of the background levels. So we're not thinking that this is a major cause of mortality, but does have an influence. Also, we looked at the effect of this koa moth defoliation on the growth rate of these trees. So this is the relative growth rate of the basal area. And you can see that the higher the defoliation category, remember 4 is more than 90% of the canopy that was defoliated, we do see a reduced growth rate. The lower the defoliation, the higher the growth rate, and this category medium, which is 50 to 90% of defoliation, is kind of in between. So the moth outbreak is affecting the growth rate of the trees, and we wouldn't have been able to get this data unless we had these long-term plots, because we had the trees already tagged and marked. Other studies that want to do this kind of thing on this kind of moth, or many other examples of disease and outbreaks, you're sort of behind the curve if you don't have the data beforehand as a reference to compare. And that is one of the beauties of long-term plots, is you're ready and waiting for these kind of events to happen. So for the koa moths, we did see that trees with higher levels of defoliation had lower growth rates in the future, and potentially higher mortality, although, as I'm mentioning, our number of trees that died is pretty small. And this complements research that Banco et al. And a large group of people did at Hakalau. And what they found there is that this koa moth outbreak was basically a bonanza for birds, for bats, for parasite wasps. There was a lot more food to eat. And so it did have ripple effects in the food web. They also looked at the effects on nitrogen cycling, because you're getting this huge amount of litter falling down all at once. And while there was a nitrogen pulse, remember koa is a nitrogen fixer, so it tends to have higher nitrogen concentrations in its leaves than many of our other native trees. That effect on nitrogen cycling was pretty small and short-lived, so that this is more like a blip in the forest rather than a major restructuring event in terms of nutrient cycling. What we found is that the long-term damage to the forest is relatively slight, having the before and after data, and really only affected a few trees in terms of mortality, although almost all the trees were defoliated. And therefore, we're thinking that these koa trees are really relatively resistant to this koa moth. Remember, the moth is endemic. The trees seem to be able to handle this kind of defoliation. And that's encouraging, because there may be other events also in the future, like hurricanes, that could also cause this large defoliation events. The hurricanes might have other kinds of damage that, if it's more severe, might have bigger effects on growth and mortality. But losing the canopy doesn't seem to have, it has effects, but it doesn't seem to have major effects that we really need to worry about the health of our Hawaiian forest for. Okay, so that's the first story I want to tell. The second story is about variation in climate from year to year. And I think everyone, if you've been in Hawaii and you've experienced time in the forest, know that there's extreme variation in climate variables from year to year. I'm showing two here: temperature, mean annual temperature, and mean daily rainfall. And the zero line is sort of the mean of the means, basically. And so being below this zero line means you've got a drier year than a long-term average, or above means a wetter year, sorry, this is temperature, a colder year or a warmer year. And that's the, you can see that for both temperature and for rainfall, there is a lot of variation from year to year. For Māmalahoa and Puʻuwaʻawaʻa, we don't have as long climate records for this analysis as we do for the two larger plots at Laupāhoehoe and Pālamanui. So the climate variables that we measured and focused on for this analysis were temperature, rainfall, short and long wave solar radiation, relative humidity, and wind speed. And we wanted to ask, how does this climate variation interannually affect tree growth and mortality over time? And how can we use this information to better prepare for climate change in our forests? So on the left here is the similar kind of graph showing these anomalies, or relative to the long-term means. And we can see that there's variation here in relative growth rate. This is change in diameter is the top panel. The middle panel is the growth relative to biomass change. And the bottom one is the mortality rate, the proportion and percentage of trees dying per year. And you can see, again, among the different sites, there's variation from year to year. It's not flat. And we wanted to see, how is this related to climate? And we hypothesized that these climate-driven patterns in the relative growth rates and mortality would be determined by a dominant limiting environmental factor, that one of the climate variables was probably the most limiting and most controlling of the interannual variation in growth and mortality. And also we hypothesized that species would diverge, and that the stand level, which you're seeing here, is one way to look at it, but so is the individual species way. So we wanted to see how these differences in growth and mortality measurements are related to climate. So we did an analysis that I'm not going to go into detail here, but I'm happy to answer questions if you want more information. But it's called ClimWin. And what the ClimWin does is it looks for correlations. You need to have long-term data of some kind of process. In our case, it was the stem diameter. So we could calculate growth. And then also alive or dead, so we knew what trees died. But in this case, I'm focusing on the growth analysis. And then you need to have long-term climate data. And it matches the two up so that it tells you which factors, that's this column here with the best climatic predictor, best relate to the relative growth rates of the forest or the species. And then also on the right side, where it shows these two different windows, that is really useful because it tells us about these lag times. So if there's a drought today, and a low rainfall period, it's not like the trees in the forest die the next day. Okay, there's a lag time. And what is that lag time? How can we look at that? And this is what this analysis does. So for Laupāhoehoe, at the forest level, it determined that the minimum temperature is the one that the forest is most sensitive to that. The forest growth is most sensitive to minimum temperature, and the minimum temperature is occurring at the nighttime. And that there's a 6 to 10 month window, so that the temperatures experienced today will be seen in the growth of the trees 6 to 10 months down the line. So they're not growing immediately in response to the conditions. Their growth rate that we measure now is due to what happened 6 to 10 months ago. Okay. And then for Pālamanui, our lowland dry forest, rainfall is the variable that is the one that's controlling the forest growth the most. And then there's a 3 to 4 month window. So a dry period, a low rainfall, for example, will affect the growth of the trees 3 to 4 months later. That's when we can pick up the signal of that dry period. And you can see also that within these sites, we focused on some of the key species, and the species do differ. Not every species is the same as the forest level on the whole stand level, which is taking all the trees into account based on their abundance and the different species. So there's a couple factors that are important: rainfall, photosynthetically active radiation, relative humidity, and then temperature are factors that seem to be controlling different species growth rates in these forests. So in summary about the interannual variability, we know that climate is changing. There's been very good work on that to see that we have rising temperatures, both the mean, the min, and the max temperatures in Hawaii. And in general, in a lot of cases, we have declining precipitation. And that's going to influence our forests. The greater nighttime temperatures are going to increase plant respiration. And because the montane wet forest at Laupāhoehoe is more sensitive to temperature, those are the ones that are most likely going to be affected by these higher minimum temperatures. And that increased plant respiration tends to, other studies have shown elsewhere, stress out plants more. They decreases the amount of carbon they gain through photosynthesis, decreases their growth rates, and can cause changes in the long-term carbon balance of these forests. The rainfall is going to have a larger impact on our dry forests than our wet forests, because the dry forests are much more sensitive to rainfall, dry periods, and droughts. And we see that different species are different in their susceptibility and sensitivity to climate variables. Ohia was most sensitive to relative humidity, which is an integrated variable that is related to both temperature and rainfall. Koa was more sensitive to temperature, and the dry forest dominants, Alahe'e and Lama, were very sensitive to rainfall. Taken together, these rising temperatures and lower rainfalls that we're expecting for Hawaii could have a large influence on our carbon storage. How much CO2 is being stored in the vegetation versus being released into the atmosphere. This is being studied globally. And there's been studies to show that climate change is affecting this in many other tropical forests. And we think there's a high potential for that in Hawaiian forests as well. And it may also have effects, these climate change variables may also have effects on invasion and what other species may do well and be strong competitors in our native Hawaiian forests. Okay, a third story I want to tell is about pig damage. And we looked at this in relation to hapu'u, tree ferns at Laupāhoehoe, where the hapu'u are very dominant. It's essentially a tree fern forest. It's a hapu'u forest. There's more hapu'u than any other stems there. There's about a third of the stems are hapu'u of the 3 different species. And there's also a lot of pigs in the Laupāhoehoe forest. And the pigs like to eat the hapu'u. They like to push it over, suck out the starchy core, make holes that fill up with water that can breed mosquitoes. And I think we're all sort of familiar with that story. But here is examples of pig damage We categorized it as light, moderate, or heavy. This A here is moderate, and B here is heavy damage, where the tree fern was totally pulled over and has died. So Molly Murphy, now Molly Winters, did this as part of a PIPES project and wrote it up as a study. And we looked and saw that characterized about 438 different tree ferns and looked at the number of individuals that were damaged, either as light, moderate, or heavy. And you can see that especially for the main hapu'u, Cibodium glaucum, that one is the favorite, but also the Cibodium menziziae, the hapu'i'i, also has some serious amount of damage from pigs. We determined, based on the data collected, that about 13% of individual tree ferns are damaged over a 1-year period. So you multiply that out, and you can see that pigs are going to have an influence on this forest to a great extent, because their populations, as they increase or change, are going to affect more and more of these trees. And that has an influence on the survival of these trees. On the right here, Chamasoid, there's not many individuals in the forest, and they don't get a lot of damage, but the two other hapu'u species do get significantly more damage. And when there's damage, when they're in the moderate to heavy damage index classes, the survival probability is reduced. And other data that I'm not showing here, we also have reduced growth for these species. Okay. On the flip side, the hapu'u that were completely down or that were sort of leaning tended to be substrates for more native woody seedlings. So there was kind of a little bit of a silver lining to that those were good substrates for native seedling recruitment. We've made observations now that the Australian tree fern is starting to get into the HIPPNET plot at Laupāhoehoe, and doesn't seem like the Australian tree fern has very much pig damage at all compared to the hapu'u. And Carl Spinger, who's a intern from Germany, that's with the Forest Service now, is here for 6 months, and he's starting a new project to compare the tree damage on the Australian tree fern versus our native trees. But what this points to is this real need for fencing and dealing with some of these pig issues to protect our forests and our watersheds. The last story, a little vignette I wanted to tell was about weeds. And admittedly, we haven't been monitoring the weeds in an incredibly effective way. We set up these plots in native dominated forests, and we wanted to focus on measuring the native species. But we did take data on the weeds in our forest spot. So this is the at Laupāhoehoe, this is the grid that we have with the 4-hectare plot, and you can see some of these weed species show up more than others. The reason why this data over time isn't like super great is because we when we had the resources, we would try to manage the weeds and pull them out, because we don't want to be following a forest that's just full of weeds and just measuring the weeds over time. We want to try to mulama and help these forests get as healthy as possible. But it does sort of point to us what are some of the weeds to watch and look out for, and where we might need to put more resources for management. At Laupāhoehoe, definitely the Himalayan raspberry is one that is quite abundant, can be abundant, as well as the smartweed, which tends to, the smartweed has a strong interaction with pigs where there's wet areas where there's pig disturbance. the smartweed increases, and so does strawberry guava. So does the Rubus ellipticus, the Himalayan raspberry. Data from Kapono Aguirre, who's a master's student here at UH Hilo, is showing that at Laupāhoehoe, almost all of the scat is just full of Himalayan raspberry. So both of these species are strongly interacting with the pigs. See, I had one more slide, but I guess it didn't come up here. At the other sites, there's also weeds that are important to watch. And these are some of the grasses as well. And we need to watch those, especially because of fire risk. But in summary, these long-term permanent plots are really valuable. They can tell us a lot of detailed information on key scientific questions, about dispersal and community assembly, but from a more local perspective, they allow us to be an important baseline for looking at fine scale patterns and for emerging conservation challenges, such as new diseases, animal incursion, and those kinds of things, as well as being a really sensitive indicator to understanding what is our forest's responses to climate change and what can we expect in the future. We would love it if more people took advantage of these plots and the long-term data sets. That's why they're there. There's a considerable amount of work that goes into maintaining them, collecting this data, curating this data, measuring tens of thousands of stems every few years is just a lot of work. And the data management side is quite intensive. And we'd really like it if people use this kind of data. So please contact us if you're interested in that or have other kinds of questions that maybe we can address with these long-term data. So I think that's my last, oh wait, somehow, yeah, my other weeds here that I guess got mixed up in the slides, but in Pālamanui in the dry forest, the haulikoa and fountain grass are the weeds that we want to watch the most. And in the Puʻuwaʻawaʻa sanctuary, there's other weeds such as banana poka and the dry woodland silk oak and fountain grass. So with that, I want to mahalo many people and thanks many people for funding as well for all different parts. And I'm happy to take questions.
Mahalo for that talk, Becky. I feel like I've learned so much just in the short amount of time that we've had you speak today. And I'm super excited to have these data sets and the research that's going to come from that in the future. Does anyone have any questions? Please feel free to unmute and turn on your video if you want to talk. We have about 15 minutes for questions and answers. Go ahead, Chuck.
Oh, thanks. Great talk, Becky. That's every time. I don't know how many times I hear talk from you. I always learn something. So
Well,
that was awesome. And I was really happy to hear you say that the koa looper outbreak didn't seem to have like a long-term negative effect, at least on the health of the koa trees. I know that in on other islands they've had similar defoliation events with koa, and what I'm about to say is anecdotal, so I'm just curious if you've noticed similar patterns in your plots. I know that there was a big koa moth outbreak in early 2000 and I think it was 2003 in Kipahulu Valley on Maui.
Okay.
And you know, they didn't have the benefit of all of these, like, you know, pre-established plots to look at health, mortality, vegetation changes. But anecdotally, it seemed that following that outbreak, there was a explosion of clydemia in the
Mm,
understory, you know, particularly in the mesic zone of the forest. So the 2,000 to about 4,000 feet elevation. And people were attributing that to the possible, you know, flooding, alteration of the light levels in the understory. Clydemia was just like, you know, the disturbance adapted seed bank weed, just ready to jump in and take advantage of that. And it didn't occur to me that maybe the COA nutrient pulse might have contributed to its success. So this is my long-winded way of saying, did you notice similar responses to the understory weedy vegetation
uh,
when COA was defoliated like that?
there was, let me go back. There was definitely, I think a little bit more of the Himalayan raspberry, but we don't measure it every year, so uh we didn't notice like clydemia or those effects really, but just because it wasn't it's just not super abundant in our plots. I think if those species are close by and ready and waiting, it could easily happen. So I think just the fact that these plots are higher elevation with less weeds, we didn't see a very strong effect, but I don't see why that wouldn't happen uh, if the weeds were already there. I think the changes in light levels and things like that would give them a huge advantage. And yeah, probably this nutrient pulse could also give them a huge advantage.
Okay, well, I'm glad you didn't have Clydemia ready to exploit that
Yeah,
disturbance regime. But anyway, yeah, I
yeah.
think they were
And yes,
similarly noticing that the core. Sorry.
Stephanie put Jelinek put a paper in the chat because she's also looked at this. Do you want to add anything, Stephanie?
I think Chris Balzati and Greg Asner did a study showing, I think the take-home message was that there was an increase in strawberry guava in Laupāhoehoe, but only where strawberry guava was already present. And
Yeah.
they used LiDAR for that rather than plot network data. So I haven't read that paper in many years. So I would, I guess, probably just take a look at how they ground truth that.
But yeah, I think it's like if the species are ready and waiting, could easily take advantage of it. If they're not there, they're probably not going to come necessarily for this shorter term pulse.
Agree.
Another argument for very active management.
Of
So
the weeds. Yeah,
yeah,
keeping the weeds under control. And
great,
then
great.
it's same with a hurricane. If we get a hurricane come and it opens up the canopy, I think the same kind of effect could be happening.
So Becky, I had a question. Have you used your data at all to look at rapid HETF and like longer term trajectories? Similarly, I guess with things in the understory making their way to the canopy, or how rot is affecting these forests?
So far, the rod's like moving up, but it's not really gotten to our plot yet.
Oh, nice.
Um, assuming that will happen soon, but it's not really what we want to happen. So we need to look at this newest census data, which we haven't done. We're still finishing up this third major census of all the stems and to see what the ohia mortality is and if it's increased at all.
Well, thanks for the talk, Becky.
Other questions? or thoughts?
Hey, Becky, this is Sharon.
Hi, Sharon.
Hey, great presentation. I'm kind of looking at a different thing of with how is this linked in with neon data, with all these other along kind of the approach of monitoring climate data, all the different monitoring efforts on the landscape. Is this linked in with this? Could people go someplace and access data from both areas and across those areas?
Well, so it's a very long story, but I mean, this was originally going to be the neon site at Laupāhoehoe, which would have taken advantage of these plots being already set up and the long-term data. And for various reasons, relative to the amount of line power needs, this site just wasn't going to be feasible for the neon site. So initially they would have been one-to-one correspondence, and the neon site would have added more onto this. Our Laupāhoehoe plot, the Laupāhoehoe plot. The neon site is in Puʻuwaʻawaʻa, which is a similar forest type to the Laupāhoehoe plot, and I think there's a lot of comparisons that can be done. The measurements that neon takes are a little bit different. They're not as intensive on the vegetation, but they have a lot more ecosystem level measurements. So they're complementary in looking at similar forests, and some things could be compared, but not the same. Things are not exactly at the same scale.
Cool, thank you. It's good to know. And is this data, what is it that is this data from HIPPNET pulled into other? And I'm sorry, I had to step away. Maybe you mentioned this previously. Is it pulled into other areas, like the climate portal?
Yes, it's part of, well, the climate data is part of the Hawaii Data Climate Portal.
Got it.
Vegetation data, we have a form through the Smithsonian website that comes to us and then writes a paragraph why you'd like this data, and then we can share it if it's appropriate.
Great.
And the climate data is all linked in with Mesonet and the Hawaii Climate Data Portal.
Okay, wonderful. Thank you.
And there's a webinar on that tomorrow on the Hawaii.
Oh, that's right. Thank you. Yes.
People are interested in how to use that. And so, yeah, if you want the forest climate data, that's going to be the best way to get it.
Cool. Great. Thank you.
Other questions?
Oh, Chuck has another question right now.
Sure.
I think I know the answer to this one, but what are the limitations to setting up similar plots like this on some of the other Hawaiian islands?
Funding is a big one. That's like one of our biggest challenges, because it's hard to get funding for monitoring. But the value of the monitoring, the data becomes so much more valuable the longer term you have it. And it takes a lot of labor. So to do all 4 of these plots, to do a full census of all 4 of these plots takes about a year of 3 to 4 people crew. So it's a lot of work, and getting the funding for to do that is kind of the biggest challenge as well, which we're continually facing and trying to be as creative as possible.
That's what I thought.
So if anyone is interested in the talk tomorrow, Sharon just put the information in the chat.
Oh, yeah.
So please grab that before the end of the webinar. We also can end it right here, unless anyone has any last questions. Oh, one new message. Great talk, Becky.
Yeah, thanks so much for coming, everyone. And please do reach out if you have more questions. Susan's here. She's also part of this work, and Forest Service has been instrumental in getting this done, and is really the host of this work. And yeah, please reach out to us if you have other questions or have ideas or ways you think we can, ways you see, we're really open to all kinds of ideas. All right.
Dustin.
Thanks,
You.
Becky.
Appreciate it. Thank you for coming.
Thanks, Becky.
Okay.
Perfect. Thank you for coming, everyone. We do have our September webinar on the 18th, and that's going to be Cheyenne Perry on the Mauna Kea Watershed Alliance. So look out for that information, but also got the information for the talk tomorrow. Again, mahalo, Becky, for your presentation. Thank you, everyone, for coming.
All right. Thank you so much.
Okay,
Aloha.
bye, everyone.